how the periodic table is from physics and makes chemistry. Biology is built from that. And that's the whole argument of what's going on. Now, we can say that in the beginning, remember this, that there weren't atoms at the beginning, but once the atoms formed, they formed according to the periodic trends. Oh, good. We are actually working. Nice. And so protons and neutrons combine to form this, and the reason why it has this shape is because of, it's 3 wide, 6 wide, 10 wide, 14 wide, because of the rules of quantum mechanics. And then this was what life had on the table to choose from, but not all of these things are available or useful. If you look at biochemistry, in biochemistry I'm always teaching about these elements, right? And life only incorporates these. It doesn't really use yttrium. Why? Why doesn't life use lithium? It's small, it's pretty abundant, So anything living only has a few possibilities, and so part of the book is why. Why do we only use a subset of the periodic table? And the main point is, there are discrete units of matter that explain how the universe works. These are atoms. They were proposed by Democritus in 400 BC, although he only thought there were 4 different kinds of atoms. We now know there are more than 100. But he was fundamentally right. He was proved right eventually. Many of these aren't very useful. There's only about 15 or 20 that are used for life. And by the way, it's these 15 through 20, which you'll be doing your presentations on. You'll choose one of them. But you have plenty to choose from. So like I said, just be thinking about that. Which one, is there one that interests you? And you can't pick like uranium. Life doesn't use uranium. But you can pick anything that life uses. And there were some that were, because there are some that were used, we're talking about now, how they're used for life. It turns out that the rules changed. And some were used for life early on, and they aren't used now. And there's chemical reasons for that. So there's change over time, and the chemical reasons are actually tied to the periodic table, which implies that any water-based life would follow these same rules, which actually does have interesting implications. It does suggest, again, water-based, maybe there's other ways to bring life together, but I would like to see it if how it works, if that's so. For water-based life, stuff dissolving in water, there's only these elements, and they can only be used in a certain sequence. There's some that you can't use right away. You have to wait. And they actually are based on chemistry and math. And so the idea of constraints comes up again. That we're constrained to use only those 15 to 20 elements. We're constrained to use them in this particular order. For some of them that have to be used early and used late. So it's the idea that there's a path that involves life, that it results in living bodies and creatures and ultimately living human minds that is in some way beginning with the periodic table. Just like with the physics, there are some numbers that we could use and some numbers that we can't use. The quantized means that there's numbers that you can't use between the two quantized values. There's also quantized elements in a sense. You can't use things in between the elements, and you can't use them out of order. And so the idea of constraints is just like we were talking about the wave being constrained by the edges of the box. Life being constrained by the periodic table is kind of like a river being constrained by a valley. I like this because it shows the idea of change over time as well. Because the river starts off, and the river can change, right? But it's always, the water's always going to flow downhill. And the river might reveal different things as it carves out the rock, but the water's still flowing downhill. And there's a way that once the water starts flowing downhill, it will stick with that. And so the question is, we see the water flowing downhill. Did it have to take that path? Or could it have taken this other path? Could it have gone to the right rather than to the left? If it's all the same rock, then it doesn't matter. But sometimes you have a really hard rock over here, and the water can never go that way. It's the idea that we have that kind of path in chemistry. And so there are kind of restrictions. I want to say, what are our boundary conditions? Just like what we have to tie down the waves. What do we have to tie down us? Well, we have the periodic table itself. And then there are other ones. The gas law. We've already used that. We will use it again on Wednesday when we get back to chapter 1. That's why we teach it to you, because it actually is a constraint that tells you how things work. Melting points and boiling points for pure substances. These are physical properties. Those are true wherever you have the same pure property in any planet. So we can actually calculate what the stars, and actually as we're looking at exoplanets, we're starting to be able to see what the melting points and boiling points are going to be the same there. And then binding constants and bond strengths. Basically what dissolves well in water is going to be true on any planet. So that's why I'm always very careful to say these are true for water-based life. And it's very important to say that we're talking about, this does involve evolution, and there is a certain amount of randomness in evolution. It's just that the randomness is not complete. And there's a debate going on, and you'll see that debate in the book. And I come down on the side of R.J.P. Williams, who basically says, yeah, origin of species has a lot of randomness to it. But he defined things that he called chemotypes, which include a lot of species. And the chemotypes are dependent on chemistry and what's available from the periodic table. And the chemotypes allow you to say the inevitable logical sequence. So what was required was the sequence of chemistry. And so what better place to talk about it than in a chemistry class? And that's why this came about. Equilibrium, thermodynamic, and kinetic. By the way, we're talking about thermodynamics. So if you're wondering why are we having to talk about this, well, it's because these are the constraints, and these will go with what you read in the book. Just to say what a chemotype is not saying the organism looks like this or the organism is this color. It's what chemistry does the organism do? What do they eat? What do they excrete? We are a chemotype that takes in oxygen and sugars and turns it into carbon dioxide and H2O. It's very reductive, and it's definitely different than the way a biologist would look at it. But yeast and humans are different chemotypes because the yeast are single cells, and we are multi-cell. And so he talks about the chemotypes, and he talks about the idea over time you have an arrow that goes with oxidation. So chemically oxidation increases, and then you have anaerobes, and the anaerobes happened, however many billion years ago. And then you had aerobes, and then you had eukaryotes, and then you had multi-cell, and then you had animals, and then you had humans. And the idea is that the old ones don't go away, but they increase in diversity and sort of make room for the new, more complex ones. So really cool. It comes from exactly the front of his book, and this is the book that basically gave me the idea to write my book. So I definitely want to give him credit. And that's why I talked about before, you're assigned to read 6 chapters of the book by the midterm, by the end of the month. So that means in a week or so, I'm going to ask you to have read 3 chapters of my book. We'll have a day where I'll do a data talk, and then I want you to bring questions. So I want you to get started on reading the book, and I want you to write down questions for me, where you'll see, I think it's even already on Canvas what I'm asking for. But in general, hopefully, I just want to know what you're curious about. At the end of the course, you're going to do your own version of the data talk, where you talk about how an element works. Okay? And that brings us to where we are. That brings us to the end of class. All right, so thank you.